Could quantum processes associated with black holes create new disconnected regions of space-time? And what would that mean for information, cosmic origins, and the limits of known physics?
Well, that is the big one. We are looking at a foundational conflict right out of the gate here.
Yeah.
Because on one side, you have classical general relativity.
Right.
And that describes a black hole event horizon as an absolute, one-way causal boundary. Gravity is so intense that nothing...
So nothing light.
Right, not even light can get out. But then quantum field theory enters the picture, and it tells us black holes actually have a temperature.
Which is wild.
Yeah, they have entropy, they emit radiation, and eventually they might evaporate entirely.
Wow.
So if nothing can escape, but the black hole itself evaporates away, what happens to all the information that fell inside?
You have to go somewhere.
Exactly. That massive contradiction is what drives some of the most mind-bending, speculative proposals in quantum gravity, like branching space-time or baby universes.
Today, we are taking you on a journey to the absolute edge of physics. To give you a roadmap for this deep dive, we're going to start at the point of no return.
Right.
Classical black holes and event horizons, and then push right through into black hole thermodynamics and Hawking radiation.
Mm-hmm.
From there, we'll hit the crisis of information loss, explore the bizarre concept of imaginary time, and unpack those wild baby universe proposals.
Yeah, the fun stuff.
And finally, we'll zoom out to what a unified theory actually means for our universe, our future, and whether everything we do is predetermined. But before we jump into the physics, a quick disclaimer.
Sure.
This deep dive is an independent Cosmora HQ book overview of Stephen Hawking's black holes and baby universes and other essays.
Mm-hmm.
This is not an audiobook, an authorized adaptation, an endorsement, a complete narration, or a substitute for lawful access to the original work.
Right. The essays in this collection really serve as an intellectual map of questions.
Yeah.
They capture a specific era when theoretical physics hit a massive brick wall, and they outline the highly creative ways researchers tried to climb over it.
Okay, let's unpack this. Let's start with the classical view of that wall. When people picture a black hole, the visual is usually a giant dark sphere.
Like a hole in space.
Right, a physical object, almost like a dark star. But if we really drill down, a black hole isn't exactly a thing you can touch, is it?
No, it's not.
When we talk about an event horizon, I tend to picture a cosmic waterfall, where the water's falling faster than you can swim.
I like that. The waterfall analogy gets much closer to the truth than picturing a physical sphere.
Oh, really?
Yeah, because an event horizon is strictly a causal boundary.
Okay.
It is not a material surface. There's no glowing membrane. There's no solid shell.
Yeah.
If you were falling into a supermassive black hole...
Which sounds terrifying.
Yeah, very bad day. But depending on its size, you might not even notice the exact mathematical moment you crossed it.
Wait, really? You wouldn't feel a bump?
Nope. It simply marks the geometric region in space-time where the escape velocity exceeds the speed of light.
I see.
Because the speed of light is the absolute speed limit of the universe, any signal you try to send outward, like light, radio waves, anything, it's dragged back inward.
Because space itself is moving.
Space itself is effectively flowing inward faster than light can travel outward.
So it's a boundary of cause and effect. Whatever happens inside cannot cause an effect outside.
Yes, exactly. And we have to clearly distinguish this causal boundary from the classical singularity at the center.
Right, because people mix those up.
All the time. The horizon is just the point of no return. The singularity is the infinitely dense point at the center where the classical physics of space-time breaks down entirely.
The math literally stops working there.
It totally stops. But the horizon itself, that was always considered a one-way street. Nothing leaves.
Until the story takes a massive pivot.
Right.
Because Jacob Bekenstein and Stephen Hawking realize that this one-way street somehow has thermodynamics. They proposed that a black hole's horizon area is proportional to its entropy. But why does a black hole need entropy? Usually when I think of entropy, I just think of a messy room or heat dissipating.
Well, the messy room idea is how we usually teach it in high school. But in physics, entropy is a measure of hidden microscopic information.
No.
It implies that a system has an enormous number of microscopic degrees of freedom, ways its internal parts can be arranged.
Even if it looks uniform from the outside.
Exactly. By proving a black hole has entropy, Bekenstein and Hawking showed it isn't just a simple, smooth geometric pit.
Right.
It has a staggeringly complex internal quantum state.
Even though we can't see it.
Right, even though the only things an outside observer can measure are its mass, its spin, and its electrical charge.
But if it has entropy, the laws of thermodynamics say it must have a temperature.
Yes.
And if it has a temperature, it has to emit heat.
It has to glow.
But we just established the horizon is a one-way causal boundary.
I know.
How can a boundary emit radiation? I know pop science usually explains this with the vending machine visual.
Oh.
You know, particle-antiparticle pairs pop into existence right on the edge. One falls in, the other escapes, and boom, radiation.
Yeah, we really need to move away from that particle pair analogy.
Oh, really? Why?
It is an incredibly common heuristic. I mean, even Hawking used it in the book to try and explain the math in simple terms.
Right.
But it does us a disservice as a literal derivation. Ordinary matter is not simply escaping or climbing back out through the horizon.
Okay, so if it's not a particle throwing its twin into the abyss to escape, what is actually happening?
It comes down to quantum field theory in curved spacetime.
Okay.
In quantum mechanics, a vacuum is never truly empty.
It's bubbly, right?
Yeah, it's a seething, dynamic state of fluctuating fields.
Yeah.
When a massive star collapses to form a black hole, the geometry of space is changing violently.
Because of the intense gravity.
Yes, because of that extreme curvature and dynamic change, what a distant observer considers to be an empty vacuum does not match what an observer falling into the black hole considers an empty vacuum.
Wait, they disagree on what empty space is.
Exactly. The differing definitions of the vacuum state mean the distant observer detects an approximately thermal flux of energy.
Wow.
So the radiation is generated by the quantum fields in the surrounding curved spacetime far outside the horizon.
Outside.
The black hole loses mass and energy radiates away, but that classical one-way rule for anything already inside remains unbroken.
Okay, I want to ground this in reality for a second. We've done the math, the theory is beautiful. Have we ever pointed a telescope at a black hole and seen it glowing with Hawking radiation?
No, we haven't.
Never.
Never. Hawking radiation is a robust semi-classical prediction, but it has never been directly detected from any astronomical black hole.
Why not? If they're glowing, shouldn't we see it?
Well, for the stellar mass or supermassive black holes we can actually observe, this predicted temperature is a tiny fraction of a degree above absolute zero.
No.
It is far colder than the cosmic microwave background radiation of the universe.
So it's drowned out.
Completely. The faint glow is entirely overwhelmed by the heat of the rest of the cosmos. So it stands as a brilliant theoretical triumph, but not an empirical detection.
The terrifying thing about this triumph is that it accidentally breaks physics.
It really does.
It creates the information paradox.
Because the radiation Hawking calculated is purely thermal.
Right.
It has a temperature, but it carries no detailed structure.
Let's make this tangible. Imagine if the universe could literally forget things. Not just misplace them, but delete the fact that they ever existed.
Which quantum mechanics hates.
Exactly.
Okay.
Let's say I take the entire Library of Congress, right? Every book, every historical record, millions of pages of incredibly specific, detailed information.
Okay.
And I throw the whole library into a black hole. It crosses the horizon. The black hole gets slightly heavier.
Mm-hmm.
Over an unimaginable amount of time, the black hole evaporates completely through Hawking radiation until there's nothing left. The radiation that came out was blind heat. Where did the books go?
Well, if the black hole evaporates completely into that purely thermal radiation, the original detailed quantum state of the library appears to be entirely erased from the universe.
I'm going to push back on that because I feel like this happens on Earth all the time.
Yeah.
If I take a single book and throw it into a campfire, it burns. The book is gone.
Sure.
But physics tells us the information is technically still there in the smoke, the ashes, and the heat.
Mm-hmm.
It's incredibly scrambled, but it's not erased. Why is a black hole different than a campfire?
That campfire analogy is exactly what physicists point to when trying to resolve this, because when you burn a book, the process follows unitary quantum evolution.
Unitary evolution.
Yes, that is the bedrock rule of quantum mechanics. Information must be preserved in principle. If you had a magic supercomputer, you could measure the exact trajectory of every molecule of smoke.
Every flake of ash.
Exactly, every flake of ash, and perfectly reconstruct the book. The information is scrambled, but it exists in subtle correlations.
But the black hole isn't producing smoke.
Right. A purely thermal quantum state, which is what the original calculations showed, is fundamentally different from scrambled smoke.
How so?
It is uncorrelated. It is what we call a mixed state. If you run the math backward on purely thermal radiation, you don't get the Library of Congress back.
You just get what?
You just get a generic black hole. The unique history of what fell in is gone. This is the paradox. General relativity says the information is trapped, quantum field theory says the black hole evaporates into featureless heat, and quantum mechanics demands you cannot delete information.
One of them has to be wrong.
One of them is wrong.
Now, strictly speaking, the physics community hasn't just been sitting on this since the 90s.
No.
As post-publication context, we should note that modern research, things like the page curve, holographic principles, and replica wormholes,
Right.
those strongly point toward the information being preserved.
Yes, as later context, theoretical physicists have found sophisticated mathematical ways that the information might actually escape in incredibly subtle correlations within the radiation.
So it might be closer to your campfire analogy after all.
It might be, but we cannot claim the paradox is universally resolved.
Hey.
It's still one of the greatest engines driving theoretical physics today. And back when Hawking was writing these essays, this apparent erasure forced physicists into some highly speculative, wild escapes.
Which naturally leads us to baby universes.
Ah, yes.
If the math refuses to let that information just disappear, but the black hole is completely evaporated, that information has to be somewhere. Does it literally break off a piece of reality and take the information with it?
Well, in this context, a baby universe is a mathematical model-dependent proposal.
Okay.
It involves a new or disconnected spacetime component or a fluctuating topology. Imagine the fabric of spacetime developing a little branch that pinches off from our main universe.
Like a budding plant.
Exactly. The math of quantum gravity might allow for these topological fluctuations at the microscopic scale. So, local observers in our universe see the black hole evaporate and the information lost.
But in the global picture,
Right? In the global overarching structure of reality, the information went into this disconnected baby universe.
so on behalf of everyone who has ever watched a sci-fi movie,
I know where this is going.
are we talking about portals? If I fly a spaceship into a black hole and survive a really bumpy ride, do I pop out into a brand new universe with purple skies?
I have to stop you there because science fiction has totally skewed our view on this. Black holes are not confirmed portals.
No interdimensional travel.
You cannot fly a spaceship through them to another world. The classical tidal forces inside an ordinary astrophysical black hole are entirely lethal.
Spaghettification.
Right, you would be stretched into a string of atoms long before you reached any hypothetical portal. Furthermore, baby universes have never been observed.
Never.
Never. They are a conceptual, mathematical possibility explored to see if quantum evolution could remain consistent. It's about mathematical consistency, not interstellar tourism.
No vacation homes in the baby universe.
Got it.
No vacation homes. But speaking of concepts that sound like science fiction, we also have to tackle imaginary time.
Oh, imaginary time?
Yeah, Hawking and James Hartle use this in their no-boundary proposal for the origin of the universe.
Yeah.
What exactly is imaginary time? Is it a dimension where time runs sideways?
The word imaginary carries a lot of unfortunate baggage. It is not a hidden world, a fantasy time, or an alternate psychological experience.
Okay.
It is strictly a mathematical representation. It's a Euclidean technique used in quantum theory. Without getting completely bogged down in the equations, if you substitute ordinary time with imaginary time.
Multiplying the time variable by the square root of -1.
Exactly. The minus signs in the geometry equations become plus signs.
What does changing a minus sign to a plus sign actually do?
It makes time behave mathematically exactly like a spatial dimension. It removes the sharp boundaries and singularities.
So if we treat time exactly like a spatial direction, like moving north or south, does that mean the Big Bang isn't a sharp starting line anymore, but more like the North Pole? There's no boundary north of the North Pole. The Earth just curves.
That is a brilliant way to conceptualize it. In this model, the universe in imaginary time is finite, but it has no boundaries or edges. There is no singularity.
So no chaotic edge at the Big Bang where the laws of physics break down.
Right. It allows physicists to calculate a quantum wave function of the universe, but translating that mathematical trick back into our physical, everyday reality,
Where time very clearly marches forward.
yes, where we get older, that is a complex interpretive step. Doesn't mean our real-world experience of time is an illusion.
If theoretical physics is reaching a point where we can mathematically model the smooth birth of the universe without a starting edge, and we're modeling the ultimate fate of black holes, it feels like we are inching toward a unified theory, a theory of everything. But if we find the master equation that dictates how all particles interact, what does that mean for us?
That's the big philosophical question.
All right, does a unified theory predict my every decision? Are we just complex biological machines playing out an equation we could technically solve?
Hawking addressed this directly, using a fantastic analogy. Chaotic weather.
Weather.
Yeah. A unified theory unifies the fundamental interactions, gravity, electromagnetism, and the strong and weak nuclear forces.
It provides the base rules.
But knowing the rules of chess doesn't mean you can predict every move of a grandmaster tournament.
Oh, I see.
A unified theory does not eliminate emergence, quantum probability, chaos, or computational limits.
So even if we have the master equation for reality, we still can't predict if it'll rain next Tuesday in London with perfect accuracy.
Exactly, because of the butterfly effect. In complex, nonlinear systems, an incredibly tiny change in the initial conditions, a butterfly flapping its wings grows exponentially into a massive change, like a storm.
So applying that to people.
To predict a human being's actions, you would need to calculate the interactions of trillions of particles perfectly, which is computationally impossible.
Not to mention quantum indeterminacy.
Right. So discovering the bedrock equations of reality would be a profound triumph, but it would not predict every human decision.
Biology, psychology, and our practical free will are safe from the equation.
They're safe.
But what about the universe itself? Does this unified framework tell us how the entire story ends?
We have to extrapolate based on our current cosmological models, which show an accelerated expansion driven by dark energy.
The universe is getting bigger, faster.
Yes. Extrapolating into the incredibly distant future, and keeping in mind this is a conditional, model-dependent guess,
Right.
the stars will eventually exhaust their fuel and cease forming. Our universe will go dark, it will be dominated by remnants and massive black holes.
Very cold, very lonely era.
Yes. And if Hawking's semi-classical calculations hold over those immense, unfathomable timescales, eventually, even those supermassive black holes might evaporate away into thermal radiation.
So the whole universe just fades out.
The universe essentially dissolves into a thin, cold back of photons.
It's a deeply humbling thought. And we can't talk about these humbling cosmic concepts without talking about the person who brought so many of them into public consciousness.
Absolutely.
What strikes me as a profound, almost counterintuitive insight here is how Hawking's life dismantles the classic myth of the lone genius.
It really does.
We always picture Einstein alone in a patent office, or Newton isolated under an apple tree. But Stephen Hawking physically could not be a lone genius.
No. He had a highly unconventional path driven by fierce intellectual independence, but you're absolutely right. Because of his motor neuron disease, his reliance on a massive community was highly visible.
It was front and center.
What his life really highlights is the profoundly human, collaborative element of science. He relied on complex technological assistance, robust social structures, dedicated caregivers, and a brilliant network of collaborators.
Physics stands entirely on its own mathematical merit. It isn't correct or incorrect because of his physical condition.
Right, the math has to work.
But his condition forces us to acknowledge that scientific advancement is a communal human endeavor.
We have to share that credit widely. People like Roger Penrose, who worked with Hawking to prove the singularity theorems,
Jacob
Bekenstein, who first championed black hole entropy, James Hartle, who co-developed the no-boundary proposal. Hawking's unique genius was in his ability to synthesize these incredibly diverse fields, quantum mechanics, thermodynamics, and relativity.
And his unparalleled public communication skills.
Exactly. He believed advanced science shouldn't remain the private property of specialists locked away in journals.
Because these ideas affect how all of us view our place in the universe.
They belong to everyone.
But as we wrap up this deep dive, we need to draw a strict line between what is fact, what is predicted, and what is total guesswork. Let's look at the evidence ladder. Where does the science actually stand today?
Okay, rung one of the evidence ladder, astrophysical black holes. These are strongly established by observation. We have measured gravitational waves from their collisions. We have tracked the orbits of stars whipping around them at the center of our galaxy. We even have horizon-scale imaging from the Event Horizon Telescope.
So they are absolutely real.
They are real. Rung one is solid ground.
What about rung two?
Rung two, Hawking radiation. This remains an undetected theoretical prediction.
Undetected.
It is mathematically robust, it beautifully unites gravity and thermodynamics, but because it is so incredibly weak in astronomical black holes, no telescope has ever seen it.
And the final rung?
Rung three, baby universes. These remain entirely speculative.
Just ideas on a chalkboard.
Exactly. They are mathematical tools and frontier proposals in quantum gravity, but there is zero observational evidence that they exist or that black holes create them.
The established, the predicted, and the highly speculative. It's a beautiful spectrum of how science actively pushes into the unknown.
It really is.
If this journey through causal boundaries, information paradoxes, and the ultimate fate of the cosmos sparked your curiosity, I highly encourage you to seek out lawful access to Hawking's book, Black Holes and Baby Universes, and other essays.
That's a great read.
Hearing his own voice, his distinct humor, and his unabridged arguments is a totally different experience than any summary can provide. And if you enjoyed this deep dive, make sure to subscribe, leave a comment, and share this with someone who loves staring at the night sky.
The questions we can't answer yet are just as important as the established facts we possess.
They really are. And so I want to leave you, the listener, with this exact question to mull over. If black holes can change the structure of space-time itself, where does established physics end and speculation begin?